Did everybody grab their new packet up here? All right, so there's a couple things in the packet that actually, when we get there, I'll point it out. But there's a couple things. Something was going weird that it didn't copy totally correctly, but whatever. As I've mentioned before, I try to start every unit with what I call my vocab and tech page. These are all the vocab words that you need to be familiar with, but I also like to point out the calculator skills. I think you guys know how to do scatter plots on your calculator. I think you've done least squares, regression lines, but you are going to learn how to do something called a residual plot on your calculator. You might not even know what a residual plot is right now. So, all right, unfortunately, the beginning of the notes is just a lot of the talk through, okay? So again, I know you know about scatter plots, but now we need to talk about the whole setup and the vocab from a statistical perspective. So in chapter 1, we studied relationships between categorical variables, such as does the type of beverage depend on, does the type of beverage depend on your location? Wasn't that the question I did on your test? You know, that you had vending machines in the cafeteria, the lobby, and the gym, okay? So when we do things like that, those were categorical variables, the type of beverage and the type of location. But now what we're going to do is we're going to have numerical data, and we're going to have two sets of numerical data and see if they're related. That's the difference between what we did in chapter 1 and what we're going to do now. So we call this bivariate data, and I talked about that briefly the other day when we did our opening exercise for chapter 3. To understand a statistical relationship between two variables, we measure two variables like hand span and height, like we did the other day, and we measure those two things on the same experimental unit, okay? So each one of you would have been considered an experimental unit, and on each one of you, we took two pieces of numerical data, your hand span and your height, okay? So the explanatory variable is graphed on the x-axis, and the response variable is graphed on the y-axis. Now, you guys are very accustomed to, back in algebra classes, we would call this the independent variable along the x-axis and the dependent variable along the y-axis. But in probability and statistics, the words independent and dependent have a different meaning. And if you think back to Algebra 2, we did things with probability called independent events and dependent events. And that is why in the study of statistics, we don't use these words to describe our variables anymore, okay? We will call this, instead of the dependent variable, we call that the response variable. And instead of independent, we call that the explanatory variable, okay? The response variable measures the outcome of a study. The explanatory variable may help explain changes in the response variable. All right, so I have a couple of examples here, and I said, let's identify the explanatory and the response variable. And so you can go back and use your old algebra words if you want to. Okay, you could start by saying, all right, the two things we're talking about. We have attendance at a sporting event. That's a numerical piece of data. How many people are there? Okay, the big house seats about 109,000 people. Okay, game winning percentage for the previous season. Okay, that also is a numerical variable. Okay, where, you know, did they have a 50% season where they won half the games and lost half the games, whatever. But the question is, and I'll go back, like I said, I'll use my old algebra terms. Do you think attendance depends on the previous game-winning percentage? Or do you think the game-winning percentage for a team depends on their attendance? Any thoughts?
Winning percentage depends on, no, attendance depends on.
Attendance depends on. Okay, so you view it as the attendance, and I'm making an assumption here. Attendance is going to go up if they win more games because it's more fun to watch. Okay, I agree with that too, right? It seems right. Okay, so if you felt that way, you would set this up and you would say, I think attendance depends on how many games they win. And especially the way that they're talking about the previous season. So we're talking about what happened in the past. So this is attendance, by the way. You would now be calling this the response variable, and this is the explanatory variable. We'd be saying that we think the attendance is explained by their game winning percentage from the previous year, okay? Now the other example I put here, I did it on purpose because, and I'm just gonna jump to the punchline. I don't think either one of these necessarily causes the other one, okay? Does your SAT depend on your GPA, or does your GPA depend on your SAT? Okay, I'm not sure they do, but do you think there in general is a relationship that a person with a higher SAT maybe has a higher GPA, a person with lower GPA? Yeah, okay, I think so too. Now, are there unique situations? Of course. Okay, my son, he had a really high ACT score when he was in high school. He was a little bit of an underachiever though, so his GPA wasn't as high as you would have expected it to be. Okay, and we all know people like that too, right? Super smart people who don't get great grades because they just don't like to do their homework and stuff like that. Okay, so in this situation, if you were to set this up, you would end up saying, well, should I put GPA down here and SAT here, or should I reverse it? And the answer is, it might not matter. Okay, it might not matter, and that's what this paragraph is talking about. Does high attendance cause a better game-winning percentage or vice versa? Do high SAT scores cause higher GPAs or vice versa? And what I said, and I put it in bold here, just because there's a relationship does not mean that one actually is causing the other, okay? Even this situation right here, okay? One of the things we talked about one other year, and I used this example, was when Little Caesars Arena first opened up, were people going to the Red Wings games because they wanted to see the Red Wings, or because the Red Wings were doing so well? You know why a lot of people were going? They just want to see the new arena when it first opened, okay? And that's what we call a lurking variable, which is kind of a weird phrase, but a lurking variable is when there's something else going on. There's a relationship between these two things, but maybe one's not causing the other. Maybe there's something else causing both things to happen, okay? And I said here, maybe both of these happen because you have a really smart person. So just their innate ability is the root cause of both of these things being high or low. All right, so we're learning about scatter plots, mentioned this. All right, so you guys have done R, right? Your correlation coefficient. Do you know what R is? Okay, well, I'm going to go over it anyways in case you don't. First of all, the official name is the Pearson correlation coefficient. Okay, I forget the first name, but Pearson was Pearson was the person who kind of came up with this concept. And there are other ways to calculate R with other names, and we actually will talk about a different one in the spring after the AP test. But anyways, so just to review some things. All right. Are we good? Are we all awake now? Is that a rooster crowing?
Yeah, okay. That was my username.
Okay, good. All right. So this is important here too. Linear association. Okay. The correlation coefficient should only be used to measure a linear relationship, okay? And I've talked about this since we started this class back in September, and that is one of the first things you should do with any data set is you graph it. We did that with our handspan height exercise. We made the scatter plot. We saw the dots kind of going in an upward trend. You got to graph it first, because if there's not a linear pattern in your data, then you shouldn't even be doing anything with this, okay? So it's only a linear relationship. It is a decimal value that could be anywhere between -1 and +1, okay? Now, the mistake some people make just because we're all mathematically minded, we look at a numerical scale from -1 to 1, and we think that from left to right, it's getting bigger. Well, when you measure correlation, everything measures off of 0, okay? So 0 is a very, very weak correlation. The closer you get to +1, or the closer you get to -1, it gets more, and the strength increases. Okay, +1 and -1 are both perfect correlations. It just means one is perfectly going up and one is perfectly going down, okay? If correlation is strong, the linear relationship may be used to make predictions, okay? So that's something we'll talk about when we start doing the regression line. So I gave you some examples here. Here's some diagrams, and I put here, these are guidelines. Exact interpretation of specific R values might differ. And I'll tell you what, when I was writing these notes, I Googled, okay, how to describe correlation or something like that. And different websites will set up different guidelines. They'll say from 0.7 to 1 is very strong, or they'll say from 0.75 to 1 is very strong. I've mentioned before that in this class, good or bad, it's a little vague sometimes. Some people want to know very specifically. They want to memorize. This equals very strong. This means strong. You know what? If you were taking the AP test and a correlation was 0.85 and you said strong instead of very strong, they're not going to mark you down for that, okay? These are just some general guidelines, and what I did then is I gave you a couple of pictures to give you a visual to go with that, okay? So here's an example where it's not perfect, okay? A perfect one would literally be if the points were all in a line. That would be a perfect +1. And it's not the same as slope, okay? It's related, but it's not exactly the same. Because if this was your scatter plot, that is an R value of +1, because that is a perfect linear trend. But if I drew another one over here, and I made it really steep, okay, that's also +1. It doesn't, the steepness of the line doesn't change the R value. It's, do the points lie in a line, okay? So these points aren't in exactly a line, but it's still pretty obvious that if I were to draw a trend line in, it's going right through here somewhere, okay? Because it's so obvious, that's how you know it's pretty strong, okay? Now this one, strength is almost identical, even though this one's positive, this one's negative, okay? Strength is almost identical. This one's a little weaker. Okay, there's a little bit more variation going on in here. All right, this one, you know, if you looked at that, some of you might look at that and say, well, I'm not even sure I see a positive trend. Okay, if you can cover up a couple of points and kind of see a trend, then it's there. Okay, the points that vary a little bit, it weakens it slightly. But one of the rules is if you can just cover up a couple of things and see a trend, that helps you a little bit. But every point that varies from that trend weakens the R value a little bit. Okay, same with this one. You look at it, if I kind of just cover it, it's like, okay, there's the positive, but all this variation out here is weakening it. And this one is really weak because this one you might say, well, what if I covered up these? Okay, that looks like a negative trend. But you see, if I covered up a couple here and here, I could almost make it look like a positive trend. Okay, and that's why that R value is so close to 0, because it's like, I'm not really sure anything is that specific, okay? This website, I was gonna pull it up. I will if we have a minute at the end. It's actually kind of cool. They give you, it's a matching exercise. They give you 4 scatter plots, and then they give you 4 R values, and you have to match them up. And it's just a good way to kind of get a better sense of what does an R value look like, okay? So when you go to describe a scatter plot, and I think I mentioned this the other day, this is the acronym your book uses, DOFs, D-O-F-S, direction, outlier, form, and strength. And I mentioned this the other day, and I'm going to say it again. This one, I would not do a bulleted list on this one, okay, like some of you did in the other unit with your socks, okay? Literally, direction, form, and strength. You can do them all together in one sentence. I could describe this one and say, there is a very strong positive linear association between the two variables in the scatter plot. Okay, I in one sentence, strength, direction, and trend. Okay, very strong positive linear association. Okay, and then you might say, all right, do I have an outlier? This one, I'm not sure I would call anything an outlier. If you wanted to address anything, maybe you might address this one and this one. Again, you don't have to call them outliers. What you want to do with anything that is an extreme value or an outlier in a scatter plot is you want to talk about why does it draw your attention? And what you want to say on this one is, if I did address this, I would say, and I'm just going to make this up. Let's say this was, we'll go back and say this is attendance. Oh, this was attendance over here. And this was game wins. So I would have expected, if this is my trend line, I would have expected it to be right about there. So the attendance was lower than I expected, okay? For the number of games that they won, their attendance was lower than I expected. For this one, I would have expected it to be on the trend line. So I would say for the number of games they won, their attendance was higher than I expected. And that's what you always want to do when you describe an outlier in a scatter plot. Why is it an outlier? Is the response higher than you would have expected or lower than you would have expected, okay? If you're asked to interpret your correlation, the correlation literally is a measure of strength and direction. So you could just say, if someone told you the R value is 0.8, you would say there is a strong positive linear relationship between game wins and attendance, okay? It's just literally, if someone asks you to interpret it, you are talking about the strength and direction. You should know how to create a scatter plot on a graphing calculator, but it is actually highly unlikely you will have to do this on the AP exam. I very rarely have seen that people have to do that. If you have to do a scatter plot, it'll be 5 to 10 ordered pairs, and it's going to be just as easy just to do it by hand on paper, like we did with the hand span, okay? All right, so let's talk about this. Here's an example. So I did cost versus weight. Oh yeah, I have a worksheet that it's kitchen mixers, hand mixers, and this was actual data from like a consumer report. You know what consumer reports is? Okay. They used to have to buy the books, and now you can get it online. But Consumer Reports is like one of the original things. Like if you wanted to get reviews and ratings, if you wanted to buy a refrigerator, you'd look up Consumer Reports and find out how these refrigerators were rated, or microwaves or whatever. So this was one on kitchen mixers. Okay. So what they were trying to find out was there a relationship between, does a more expensive mixer weigh more? I don't know why weight makes a difference, but whatever. But again, cost here, cost would be your response variable, just to emphasize that. Weight would be the explanatory variable. And I also want to point out what the title is here. This is really common, that how you title a scatter plot is its response versus explanatory. So it's the cost versus the weight, okay? All right, so describe what you see. So first thing I would say here, I would start by, so if you think about your DOFS, but remember, I do D, F, and S all together. There is, actually, this scatter plot shows And I'm just going to put a dot, dot, dot there, because really every time you write a description, you really should tell someone what you're looking at. So this scatter plot shows the relationship between cost and weight of 11 different kitchen mixers. Okay, and I'll just put a dot, dot, dot here. But that you really should start by telling someone what the graph is showing you. This scatter plot shows the relationship between cost and weight of 11 kitchen mixers. There is a, all right, what do you think? Does that look weak? Really weak? Strong? Very strong? No relationship? Is there, what do you see? What would you call it? Moderately strong? All right, well, you know what, I can tell you from when we did this exercise, we actually did this one year in class, the R value was 0.74. Let's see how you did according to these guidelines. 0.74, strong. You said moderately strong. You will be fine. Okay, I don't want you to feel like you have to memorize this. If you want to call us moderately strong, you will be fine, okay? There is a moderately strong. All right, you just addressed S for strength. Then what would you say? There is a moderately strong, positive, there's direction. And then give me form, linear relationship between cost and weight. And I'm sorry, my handwriting is so messy when I write this fast. Would you address any point as an outlier? That guy? Maybe, okay. So if you felt like that one needed to be addressed, what you want to, now if you actually had to pull this out, you know, put the data in your calculator, you could look at it and you can actually put the trend line in. But let's say the trend line goes right through here. Okay, let's say the trend line goes right through here. So if you were to address this guy, what would you say about it?
Lower than
all right, you want to talk about how the response variable.
it's more expensive than you think it was.
All right, so based on its weight, it's more expensive than we would have expected. Okay, so if you want to address this, you could say cost is higher than you might expect. Now, I also want to tell you, you should not feel compelled or obligated to talk about an outlier if there isn't one, okay? Don't feel like you have to find a point to say something about, okay? To be honest, I wouldn't have said anything about that point. You know which one I would have addressed? That guy. Is he kind of on the trend? Yeah, but in a scatter plot, it's not just points that fall off the trend. It's points that are far away, okay? The bottom line, what I would say here, there is one mixer that is a much lower weight and cost than all of the others. And then I would actually kind of estimate that ordered pair. And I would say, I'm going to guess, what is that, about 3 pounds and about $40. If this was on the AP test or on my test, you'd probably have the list of ordered pairs. So you could actually look at it and use a number. But when you look for outliers for scatter plots, and I think I have this somewhere. Yeah, it's right here. Outliers. Points that do not follow the general pattern or points that are far away from the others. Okay? All right. The other thing you also might want to include is, and I'm going to I'll put a little asterisk here, and I'm going to put down here. Is another thing that's nice to include is what does it mean to be a positive relationship? Okay, you're like, well, because it means it's going up. Well, what it also means is as weight increases, what happens to the response variable? How does the cost respond as weight increases? In general, as weight increases, what happens to cost? Okay, as weight increases, cost also tends to increase. And I'm going to underline that. Do not say as cost increase or as weight increases, cost will also increase. It's not true for all of them. Okay, that's the general pattern. Use a little bit of vagueness. As weight increase, cost generally increases as well. Okay, that is a great way to interpret what a positive relationship is. Okay, a positive direction. All right, so let's take a look at one more here. This one I took right off of one of the SAT practice tests. Because juniors, I thought you'd like to see, like these things, you'll see it even on your SATs. They have scatter plots. So this came off of the math SAT. The scatter plot below shows the densities of 7 planetoids. I forget what the definition of a planetoid is. You can look it up. All right, in grams per cubic centimeter with respect to their average distances from the sun in astronomical units, AUs. Describe what you see. Okay, so describe what you see. All right. If you had to, you would start by saying this scatter plot shows ... Okay, you guys, so you kind of restate what they call the stem of the problem. Okay, kind of restate, you do that in English, right? You kind of restate the question, right? Yeah, that's really what you're doing. Okay. There is a, what do you think? Give me strength. Weak, moderately weak, strong, moderately strong. There is a strong, okay, there is strength. Negative, that's direction. Linear relationship or association between density and distance. All right, so I'm going to do this asterisk again. Asterisk should be by the word negative, sorry. All right, what does it mean to be negative? As distance increases, all right, so as your explanatory variable is increasing, how is your response variable responding? As the distance is increasing, the density is going, density generally decreases. And I'm going to underline that again because you want to make sure you leave it vague. Do not say as distance increases, density will decrease. Not all the points are doing that, okay? It's a general trend. You want to keep things vague. All right, would you address any sort of outliers, extreme values, unusual points? I wouldn't necessarily by that definition, but in the category, I'll call it kind of in the category of outliers. Do you see that there's clearly like 2 separate groupings and then there's this one guy who's kind of out on his own? That's kind of a unique thing, okay? So whatever a planetoid is, why is it that there's this cluster with a low distance but a high density, and there's another cluster of high distance and low density. And then there's this one oddball in here, okay? I think if I had to describe this, I feel like that's kind of unique here, okay? I would probably say there are two distinct clusters, one with low distance and high density, and another with high distance and low density. All right, so I'm gonna, since I write so beautifully, I'm gonna read this. So this scatter plot shows distance and density of planetoids in the inner solar system. There is a strong negative linear relationship between density and distance. As distance increases, density generally decreases. There are two distinct clusters, one with low distance and high density, and another with high distance and low density. There is one planetoid that is separate from all the others, or isolated from all the others. I clearly need more space there, but I was trying to squish these formulas in and try to get it on fewer pages. Once again, what I would say on this is it's not hard. Like if you saw a question about describing a scatter plot on your AP exam on May 5th, would you now have some ideas what to include, what to write about? Hey, that's all this is. Okay, that's all I'm here for, guys, is just kind of tell you what it is you're supposed to be looking at. Okay. All right, and by the way, we're going to calculate the R value in this. So you guys said a strong negative linear relationship. Let's guess. What do we think the R value is for this? R equals, we know it's negative. What do you think? If it's strong, give me a number. Give me a number. What number do you want? Negative what? Negative 0.9? Do you agree? We're going to find out. We're going to find out. This is exciting. Question mark. We don't know. Julie might not be right. She might have nailed it. We don't know. All right. Look at these. Aren't these great? Aren't these beautiful? That one's on your formula page, I think. Somebody have their formula page handy? I think that's the one that's on your formula page. Okay. All right, so there are several different formulas that can be used to calculate the Pearson correlation coefficient, including the two shown below. Your calculator can find R for you, which I think most of you know how to do, but you guys really should know what the calculator is doing. And kind of understanding these formulas, especially this one, the one they give you on your formula page, really might help you think about we're going to talk about whether R is resistant or not, okay? And this formula will help us think about it. This formula, believe it or not, this one is sometimes referred to as the computational formula because, believe it or not, this is the easier one if you're going to do it by hand. Does it look easy? Yeah, most people look at that and go, oh my gosh, it looks so overwhelming. Now, even though we're doing it by hand, we're still going to use a calculator, but we're not going to use a calculator like just punching the data in and then saying, what's R? Boom. Okay. We're actually going to go through this. We'll use a calculator. And I know you guys can do this because years ago when I taught at LCM, I taught just a basic one semester stat course. And I had those kids doing this just on regular calculators and they were able to do it. So you guys can do this. Okay. So we're going to go through and calculate this R value. We're going to do it twice. We're going to do it. Well, actually, we'll probably do it 3 times. Because we're going to do it with this, and then we might just practice putting it in our calculators, okay? So I took this problem that came from this practice SAT, and I estimated all of these ordered pairs. So this, by the way, would be an n size of 7 because there are 7 dots on that scatter plot. There's what we have. That's what I came up with right there. Now here's the first thing that did not copy correctly when I ran this off. Oh my gosh, a whole bunch of things didn't copy on this. This is horrible. All right, the first thing is there was supposed to be a box over this that said, we're gonna just do all of this in our calculator, okay? We're gonna create these columns, but in our calculator. So you don't need to fill out the table except this bottom row. Okay, these are all gonna be sigmas. So we're gonna have to get, this is going to be, distance was on our x-axis. So these are the x's. This total is sigma x. So that didn't print like it was supposed to. Density was on the y-axis. So this box is going to be for sigma y. We're going to add up all the y values. So you're going to be putting this data in column 1. You're going to put this data in column 2. And in the next column, you can see we need x times y. Then we need x squared. So we're going to take this column and square it. Then we need y squared. So take this column and square it. And we need all of those totals. So we're going to need sigma xy, sigma x squared, and sigma y squared. Basically, a whole bunch of my graphics, because these were little graphics I had made. They didn't print for some reason. I don't know why. Okay, so put this data right here. Put your x's in your first column of your calculator or in L1 if you're using an 84. And then put your y values in L2. All right, so I'm going to refer to these as L3, L4, and L5, even though I know the Inspires don't call them lists. They just call them columns. All right, so I'm going to make me a new document. I need lists and spreadsheets. I will call this one AU for my astronomical units. I don't even know what that means, but I trust them. All right, and then I'm going to call my next column D for density. And anytime you have to enter data in your calculator, be super careful that you enter the data correctly. And for some reason, I'm like being really stupid. I keep making mistakes. It does not matter if your ordered pairs are entered in the same order, but they have to be kept on the same rows so that they are kept as ordered pairs. Does that make sense? Okay, where I've emphasized in other things that it doesn't matter if your data is entered out of order, okay? You can enter the ordered pairs in whatever order you want, but you have to make sure that the numbers stay paired up on the same rows. All right, so let me get my stuff in here. I'm usually faster on this one. Usually. All right, hopefully I got everything right. We in? Okay, good, because you only had to do one calculator, I had to do two. Okay, so this part is going to get confusing for everyone right here, because on our paper, we're calling this X and we're calling this Y, okay? Especially on the 84, where you don't name your columns. The calculator just calls everything, every column is an X for them. Just like, you know, when you enter equations, you just use X. Even if the equation on your paper had like an A or B, you just know the calculator uses X, okay? So if you need to get sigma X, what I'm going to do is I'm going to go to one variable statistics, calculate one variable statistics, and I want to do L1. All right, sigma X is 11.25. Now that one people are usually good with. Sigma X, like, okay, good, 11.25, got it. But now what I'm going to do is I'm going to do it again, but this time I'm going to go to column 2, stat, calc, one variable statistics, column 2. Now, when I tell it to calculate, it's still going to call everything X, but I know that I used column 2, so when it says sigma X, it's actually my sigma Y. Okay, the calculator will call every column X, but we know that our column, that was our Y column. Okay, so let me get Inspires caught up and make sure we're all good to go here. So menu, statistics, calculate, one variable statistics. Now, just so you guys know, you could do, if you have an Inspire, you can do more than one column at a time. You could say, I'd like to do 2 lists at the same time. What's your first one? My first one is my AU. My second one is my density. And it says, first result, what column is it going to go in? It's like, I don't care. I don't care. Just put it somewhere. Okay. And it does. So you now have 2 sigma X's. Don't do 2 variable statistics right now. Oh, I see what you're saying. So you did, yes, yes, because you could do the sigma X and the sigma Y. Yes, you are correct. Okay. The only reason I don't get into that is because we're going to be doing all of these too. So you can only do 2 at a time. The Inspires could actually do all of these at the same time. The 84s, you can only do 2 at most. So I usually just tell people just do each one separately so you don't get yourself confused. Okay. So again, the calculator is going to call everything sigma X. Well, we know the first column was our AU. The second column was our density. So there's the numbers. Okay. So what Michaela was pointing out was if you go to stat, 2 variable statistics, you could do L1 and L2 at the same time. So you could get your sigma X, you could arrow down, and you could get your, oh, you get your sigma XY too. That's kind of cool. I forgot about that. There's your sigma Y. Okay. All right. So what we're going to do now, though, is go back to your data. We need an X times Y column. So I'm going to go to the tippy top. I'm going to go to the tippy top of L3, and I'm going to tell it to do L1 times L2. And what you can do in the Inspire then, just go to the next open column and go to the tippy top, and I'm going to name it P for product. And I'm going to set up a formula. And I'm going to say equals. And I want this one to be my AU times my variable D for distance. And it just multiplied them all together, even though mine's out of focus. I don't know why. There we go. And then you could do 1 variable statistics out of that to get the total. Okay, you don't need to fill in all those numbers. I'm just going to say menu, statistics, calculations, 1 variable statistics. And I'm just going to do just that one list now. And I'm going to say I want 1 variable statistics for P, which was product. So that sigma X is now 42 I'll call it 668. Okay, we're going to have some round off error here. But the whole idea is all we really need are these totals. Okay, so I'm going to go back to what Michaela pointed out with that sigma X, sigma Y. We actually could have gotten all 3 of these on our 84s in that first step. But now we still have to go back and do it again for these 2, which is why you just tell people, just do 1 at a time. It's just as easy. So in the next column, what we need The next column, what we need is we need x squared. Okay, so you go to the tippy top and you say, I want what was in my first column, those are my x's, L1, and I want those to be squared. Okay, in the next column, I want y squared. So I'll do L2 squared. So basically, these are all the numbers that you could fill in the table, but we don't really need those. What we really need we need the sums from that column and the sum from that column. So I'm going to do stat, calculate one variable statistics. I'm going to do L4 first. So that sum is 23.7375, 23.738 then. And then I'll do one variable statistics again. L5, 134.785. So one of the reasons I like to go through this, besides the fact, it's like, you need to understand, yeah, the calculator just spits these R values out at you, but this is all the math that's going on inside the calculator. It's pretty impressive how quickly it does it, okay? I also like going through this exercise because it is good to understand that the calculator just calls everything X or Y, okay? So whatever you have on your paper, when you do one variable statistics, it's just doing that column, whether it's called X or Y or XY, whatever, okay? All right, so now we're gonna take these numbers and we're gonna put them into this formula. R equals N. What is our N size here? 7. There were 7 ordered pairs. When you deal with a scatter plot, it's how many pairs do you have? Our N size was 7. Okay, so it's 7 times the sigma XY. So the 42.668 minus the sigma X times the sigma Y. All right, so let's just get that numerator. Let's get that. So picture having just a regular calculator and doing this. Easy or hard? If you had just a regular calculator and you had to do all of this in a regular, so you couldn't even do the sigmas on your calculator. My students years ago filled in all these numbers and then they added them up and they were able to figure out their R value by hand just using a regular calculator. All right, by the way, that numerator is your indication of whether you're going to have a positive or a negative R value. Because notice the denominator, you're taking square roots. Okay, you can't take a square root and get a negative answer because you can't take a square root and get of a negative number in the real number system. So this denominator is always going to be positive, and it's the numerator that is going to tell you whether you have a positive or a negative R value. So I'm really glad that that came out to be negative because we know that this has a negative trend. All right, so let's just do the left side of the denominator. We're going to have the square root of 7, and that's going to be multiplied by the sigma X squared. So that's this guy, times 23.738 minus, now be careful on this, minus the sigma X squared. So minus the 11.25 squared. And then that gets multiplied by the exact sort of square root, but using the y's. So the n size times sigma y squared, so 134.785, and then minus the sigma y squared. And that we should be able to do in one big step, but just keep the square root separate. So I'm going to have the square root of 7 times 23.738 minus 11.25 squared. Get out of that square root and multiply by a new square root, 7 times 134.785 minus 30 squared. That's your denominator. 40.50, we'll call it 504. 41.504. So if I take those two answers, negative 38.824 divided by that previous answer. Now remember, we have some round off going here, but negative 0.94. So how was Julie's guess? Negative 0.9, negative point, not bad. Not bad. All right, I'll end with this. An interesting visual. Draw in a vertical line where the explanatory variable has its mean. Okay, explanatory variable. That is X. Let me quick do one variable statistics off of L1 again. So the mean is 1.6. Okay, so X bar is 1.6. So I'm going to draw in a vertical line at 1.6. Draw in a horizontal line where the response variable has the mean. So I'm going to do a quick one variable statistic off of L2, 4.3. So Y bar is 4.3. 4.3 would be right about here. This is Y bar equals 4.3. This is X bar equals 1.6. Basically what happens when you have a sketch like that, so I have the original graph here, but when you put your X bar and your Y bar lines in, you can almost see now why you have the negative correlation that you do, because the majority of your points will be in quadrants 2 and 4. So basically, you know that your trend line has to go in this direction. And by the way, this is also very cool. The line of best fit will always include the ordered pair X bar, Y bar. So right there, if you had to estimate where your line of best fit goes, I still don't know exactly where it goes, but it has to go through that point. It has to go through that point. All regression lines always go through X bar, comma, Y bar. It kind of makes sense if you think about it, okay? The visual idea is a nice to know, but this thing, I think they even talk about that on your formula page. Okay, that you really should know. The line of best fit will always include that ordered pair. All right, so when you look at the assignment, we started doing the calculating R here, but if you want to work on the homework, I would only do part 1 right now. Just scatter plots and general correlation, not calculating the R by hand. Okay, don't worry about that right now. Okay.